And welcome back to another episode of Stat 479, Time Series Analysis. In this lecture, we will be continuing what we did in the last lecture. Last time we looked at ACF and PACF. Today we're going to be going further into PACF, the partial autocorrelation function. So the partial autocorrelation function is a really useful tool for trying to understand time series. Now the question is, what is it actually doing? Well, we're going to look at what it does when we try to compute it for both the AR process and the MA process, and this is going to give us two different looks at each of those types of time series. So what is it going to do? Well, let's jump into the notes and find out.
And welcome back to part 2 of our lecture on ACF and PACF. Today, we're actually going to focus on the new thing, being the PACF, or the partial autocorrelation function. But first, let's see what we did last time. So last time, we introduced the idea of partial correlation, just in a general statistics context, and then defined partial autocorrelation, what we're going to be looking at in time series. We will revisit that again, just to make sure it's clear before we go through with these notes. And we also looked at the autocorrelation for the 100th time, but this time we looked specifically at what happens when you try to compute an autocorrelation for either the ARP or the MAQ process. And we found that the behavior of that function is different, and that difference can tell us a little bit, give us some ability to do inference or about our time series data that we may be studying. A lot of time series is really exploratory. A lot of this exploratory data analysis, we have some data. It is a time series. What is it? I don't know, but we have to try to figure it out. And using tools like ACF and PACF will give us some information about the time series. Now, we'll look a little bit later in this lecture at what happens when you apply these tools to actual time series data in R. But for now, we're going to jump back into the notes and we're going to look mathematically at what happens for partial autocorrelation when it is applied to an ARP or an MAQ process. So let's take a look at that. But the first thing I want to do is I want to recall the definition from last time for partial autocorrelation. So we'll say recall the partial autocorrelation or the PACF. All right. And the way we defined it last time is for xt stationary, a stationary time series. And we'll say lag h, then what we get is we get our partial autocorrelation function phi x at lag h script phi, that is, at lag h, to be just the autocorrelation itself at lag 1. And if it's not at lag 1, then we compute the partial correlation between xt plus h and xt. And the partial autocorrelation is going to look something like this. It's going to no hat there. It's going to look like the correlation between the difference between the time points of interest, xt plus h, and differencing those with their estimated value based on the intermediate data points. This is h, let's say, greater than 1. So again, where x hat t and x hat t plus h come from regressing xt and xt plus h respectively on the intermediate points, which are x t plus 1 up to x t plus h minus 1. So again, what we're doing here is we're trying to understand the relationship between xt plus h and xt. That is, we're looking at this, how the series is correlated with itself h time points apart at a lag of h. But when we're looking at partial autocorrelation, we're going to take into account all of those intermediate points. So what that means is that if the partial autocorrelation is equal to 0, it means that time point t and t plus h are only related. They're only related through their intermediate points. Otherwise, they don't talk to each other, right? It's sort of like it's a friend of a friend of a friend. They kind of know each other, but they aren't directly friends with each other. They just kind of know each other through mutual acquaintances. And that's kind of what's going on here. We have all of these intermediate points that we will be conditioning on or doing a regression against. And then instead of just looking at the correlation, the absolute correlation, we're going to be looking at the correlation between the residuals, the x minus the x hat, the fitted value, that is. So we talked about that a lot at the beginning of the lecture last time. So I just wanted to reintroduce the definition, because now we're going to start to actually compute these things, and it's going to be good to see what happens. So now what we're going to do is we're going to compute the PACF for the ARP process, and continuing our alphabet soup here of various time series jargoned acronyms. All right, so the first thing we're going to do, much like last time, is we're going to consider the simpler, I'll say. It's not simple, but it's easier than anything else, the AR1 process, because let's start with a single autoregressive term rather than having two or more. It's just going to make things worse. And yeah, as you have probably seen already in this course, presumably you're watching all the other lectures, the notation, the mathematics, keeping track of all the terms, it can get quite messy. So try to keep it as simple as possible to build our intuition about what we're doing here. But right, so what we're going to do is we're going to look at just the AR1 process. Here we have the standard AR1 process. We're going to assume, we're going to want, with, as usual, phi, my coefficient, to be less than 1 in magnitude. So we have a causal, stationary, linear process, all the good stuff that we've wanted since the beginning of the course. Now, what we're going to do is say, first, compute the correlation between xt and xt minus 2. So before we get into the partial correlation, we're just going to take the correlation itself just so we can contrast what's happening here. So when we take the correlation between xt and a time point 2 in the past, that is xt minus 2, well, what's the easiest way to do that? There's lots of ways that you can approach computing this. I think the way that is probably easiest is to just apply the definition itself, that is, apply the definition, the equation for the process itself twice, to get recursively that this is still just the correlation of phi, xt minus 1 plus wt with xt minus 2. Okay. Well, if we apply that one more time, then we can get further down into this recursion, and we end up with a phi squared xt minus 2 plus, in this case, we'll have a phi wt minus 1, and the wt is still just sitting there unchanged from the previous line, as is the xt minus 2. Now, the reason we did this is because the correlation is bilinear, and what that means, actually, it's interesting. The covariance is bilinear. The correlation would have a different denominator, I think. But in this case, it'll be okay because the two terms that were not, that's an interesting point, yeah. The two terms that were going to be, the white noise terms are just going to be 0, so it's not actually going to matter. But strictly speaking, the covariance operator, or the covariance function, is bilinear. It's linear in each of its two arguments, whereas the correlation would not necessarily be so because the denominator would change because of the variance. That's interesting. Anyway, yeah, maybe we should actually write it out as covariant, but we'll just write it out like this, because what's going to happen is there isn't going to be any correlation between xt minus 2 and wt or wt minus 1. Because remember, xt minus 2 is a causal linear process. That means it depends on white noise at time t minus 2, t minus 3, t minus 4, t minus 5, and so on. It doesn't depend on any future white noise values, and both t and t minus 1 lie in the future of t minus 2, right? If you have that kind of intuition going on. So because of the causality bit, all of this stuff ends up just being 0, and we don't have to worry about it. So to simplify things, now we just end up with the idea of, well, we can just take this and say that, well, we have phi squared here, and then the correlation of x t minus 2 with x t minus 2, which is just 1 because it's correlated 1 with itself. If we were doing covariance, we would have to compute the variance of xt or xt minus 2, which we've done before. But in this case, we can just kind of skip that and jump right down to the fact that the correlation should be about phi squared. Which does make sense, because as I kind of mentioned last time, just to make sure that we're still doing the same thing that we think we're doing, I was kind of hinting that for an AR1 process, what you should see for the ACF is a value of 1, and then a value of phi, and then a value of phi squared, and then phi cubed, and so on. This is for the AR1. And specifically when phi is a positive number less than 1, because otherwise there'd be this alternating bit where all of the odd lags, you would have a spike below the horizontal axis, but it's just easier to draw it this way. So yeah, so this kind of coincides with what I mentioned last time. Okay, so we know what we get for the correlation, or the autocorrelation. Now, in contrast, what we're actually interested in, though, is the partial autocorrelation. So for the partial autocorrelation, we have what? Well, what we have is a new equation that we're trying to compute. We're going to compute the correlation now between xt, but not xt, but xt minus phi, xt minus 1. And similarly, we're going to take xt minus 2 and subtract phi, xt minus 1. So remember, as I mentioned in the previous lecture, the coefficients we get are going to actually be the same due to symmetry. So we get a phi in each piece of our, on each half, I guess, of our correlation that we're trying to compute here. Now, this is quite it's actually even easier than the previous one, because if we use the definition of basically the one that just ran off the top of the page there, underlined in green, we know that this thing in the left argument is just white noise, WT. And we're not going to even bother touching this thing on the right-hand side, because this thing on the right-hand side lies in the past of WT. So this is just 0, right? Just to emphasize, as I kind of said above with those blue lines, right? This is causal linear, therefore not correlated with WT or any future white noise, WT plus 1, T plus 2, etc. So this is a really quick way to compute this without trying to actually write out the definitions and look at the white noise terms. It's just, okay, xt minus 2 only depends on white noise from t minus 2 into the past. Xt minus 1 only depends on white noise t minus 1 into the past. Therefore, they don't depend on WT. All the white noise has to be at the minimum uncorrelated, very often independent, but at a minimum uncorrelated. Therefore, we get a 0 there, and we're done. And we just said, oh, well, that's kind of neat. So at a lag 2, the partial autocorrelation is 0. So we can take this further, but therefore, for the AR1, we get something that's going to look like, H. We get the correlation at lag 1, which is just going to be phi, and then 0. So this is H equal to 1. This is H greater than 1. And our plot looks quite nice, because now what we'd have, I guess technically, I guess at lag 0, we would have a 1 there. But typically, when you compute the PACF, you just start at 1. You don't have a lag of, you don't consider lag of 0. Well, I guess you could probably define it just to be 1, much like we do in the ACF case. But basically what we have is we have a spike at phi here, and then we just have zeros all the way off to infinity. This is, again, for AR1. That's kind of neat, because we're not going to get all this extra junk in here with like phi squared and phi cubed and phi whatever. In this case, it's just phi, and then it's just zeros all the way, which is nice. We can use that then to identify the AR1 process. But we probably want to go a little bit further with that. So yes, what we're going to do is determine, well, basically, I guess the question we need to ask ourselves is, why did, make sure I'm doing this right. Yeah. Why did we choose xt hat to be phi xt minus 1? Right? Because if we go back to the definition, this thing that I'm subtracting here should be the fitted value. And for both xt and xt minus 2. So let's look into that a little bit further and see what's going on here. So to get this, we basically are doing regression. So we're going to compute a least squares estimator. A least squares estimator for, I guess, or a least squares estimator being x hat t for just the xt based on those previous time points. So I guess, for example, we would have something like xt hat is equal to beta hat times xt minus 1, right? Because we're trying to use xt minus 1 to predict xt. And then we would choose beta hat to minimize the least squares equation. Minimize, well, the expected value of the difference here, xt minus beta xt minus 1. I guess I'm minimizing over beta here. Let's do a double bracket just to, if OneNote decides it will allow me to erase. There we go. We'll do a double bracket here just to indicate that I'm taking the expected value of that thing, the expected value of the square of that difference. Just to make it as hopefully as clear as possible. So what do? Well, we just break up all the terms, expand the quadratic. And what happens when we expand the quadratic? Well, we get an expected value of xt squared. We get a minus 2 beta. Beta is not a random variable, so it pops outside of the expectation. And we get the expected value of xt minus 1. And then lastly, we get the last term squared, which is going to be beta squared. Expected value of xt minus 1, also squared. All right, and then we can actually compute this because assuming mean 0 for convenience, otherwise we can translate everything by subtracting off the mean and getting an extra term floating around and making things a little bit messy. It's just easier to say assume mean 0, and again, it has to be stationary, so the mean is something. You can just shift your line up and down until the mean is equal to 0. And then we can kind of proceed forward with this. Anyway, assuming the mean is 0, this first term here is just, well, the autocovariance at lag 0. That's just the variance. Then we're going to have 2 beta times, what's this? This is the autocovariance at lag 1. And then lastly, beta squared times, it's the autocovariance at lag 0 again. So that's kind of neat, right? Because then we can combine these things and we find out that what we're trying to minimize is 1 plus beta squared times k at 0 minus 2 times beta k evaluated at a lag of 1. All right, cool. So what do? Well, we can actually take a derivative with respect to beta to find a critical point. So now find a critical point as in calc class. So what do? Well, we take a derivative with respect to beta of that thing, which I'm not going to rewrite. And what we end up with is something that's going to look like 2 beta kx0 minus 2 kx1. And by setting it equal to 0, we solve and we find out that our beta hat, our critical point, is going to be what? It is going to be just kx1 divided by kx2. We know that it has to be a minimum because this thing that we're trying to minimize is quadratic in beta, and the leading coefficient is positive because the variance has to be positive. Therefore, it's a parabola, right? It's an upward, which way is it? Convex? I always forget, concave, convex. Yeah, convex parabola. So we have a convex second degree polynomial, a parabola. It has a single minimum, and we found it right here. Wait, that's supposed to be an x. I was so excited about the parabola, I forgot to say that this is kx0, and the 2's cancel out. All right, now we're pretty good to go, because we know what these things are, right? We know from before that this is just going to be rho. That is, this is just the autocorrelation at lag 1. And that happens to be just phi. That's kind of neat. So that is explaining why way up here we chose phi to be our coefficient, right? In the green lines that I the terms that I underlined in green up here at the top of the page. Okay. So that kind of makes sense, but it also just makes sense because this is intuitive, as we had that, xt is equal to phi xt minus 1 plus white noise. So if I told you that I gave you xt minus 1, how would you predict the value for xt? Well, you would multiply it by phi, and then that's a really good guess for what xt is. It's, I guess, unbiased because white noise is mean 0. So it's about as good as you can do. But then the harder question, but why did we also use phi x t minus 1 for x hat t minus 2? Because phi xt minus 1 predicts xt, but now we want to predict the previous time point, xt minus 2. So then the question is, well, why would that be the case? Well, we can do the same thing again and solve it. I kind of hand waved past this before. I said, symmetry. There's symmetry in the autocovariance function, and that's why. But don't take my word for it. Let's actually write it out and see what happens. So, making sure we're still recording. I hate it when I lose my audio. Then we're going to be back on camera mic, and it just sounds terrible. Right, so where were we? Well, we're going to do the exact same thing I did above, only I'm going to change the first t to a t minus 2. What I mean by that is I'm going to say the expected value of x t minus 2 minus beta x t minus 1 squared. All right. So what we're going to do is we're going to do it exactly as before. We want to find the beta that minimizes the expected, the squared error in some sense, I guess. It minimizes this least squares equation. Though I feel like saying minimizes least squares is already a kind of like a redundant, right? I'm finding the least squares estimator, which is the one that minimizes this thing. Anyway, we're going to do exactly what we did before. Expand the quadratic, step 1. And we get something that looks like, well, this x t minus 1. And then we get the last term, beta squared, expected value, x t minus 1 squared. And when we put this all together, we end up with a kx at lag 0. We end up with a kx at lag 1. And we end up with a beta squared kx at lag 0. And sure enough, we're going to get the exact same equation from last time that we need to minimize that same parabola. That looks like that. So again, the idea is that there is a symmetry to this. Whether I have a t minus 1 here and a t minus 2 here, or a t and a t minus 1, it's still just the stationary autocovariance. So let's look at this again. And what we see is that whether we have a t-1 and a t-2 or a t-1 and just a t, we still just get kx at 0, the stationary autocovariance, which is just the variance at lag 0, that is. So we either get 1 plus beta squared or beta squared plus 1, but ultimately it's the same thing. So by symmetry, we get the solution out, which is therefore same beta hat equal to phi in this case. And I mentioned that way back before in the first, not the first, but the previous lecture, the first of this two-part series, where I said, I am recalling that I said that x hat t plus h is just going to be some linear combination of the intermediate terms that looks like this. H minus 1, yeah. X t plus 1. And over here, we would have a t, and I claimed from last time without actually explaining it that we would have the exact same coefficients here. We're just going in reverse order. T plus h minus 1. And that's without going through it in full generality, which would just be really annoying to do with all the terms. This is really the reason why, is the fact that whether I basically go one way or I go the other way, up here at the top, I get the exact same equation that I need to solve. And there's that symmetry in the autocovariance function, which translates then into everything else. Cool, so we got that. Yeah, but this is just for the AR1 process. So what we really want to do is go a little bit further. So now the question is, what about ARP? I always want to say AARP, but that's a different thing that I don't have to worry about yet, and probably most of you don't either, especially since you're watching this on YouTube. But anyway, what we have here is we have xt is going to be white noise, WT, plus the sum I from 1 to p of phi I x t minus I, where we have that, we'll say, assume causal. So again, I don't have a nice expression for what the phi's should be to ensure causality. We just need to make sure that the corresponding autoregressive polynomial has roots that lie outside the unit disk. And that gets me my nice causal ARP process. So whatever the phi are, we're just going to assume they were chosen in a nice way to be causal, so that all of this, and then we'll have a stationary process and everything kind of makes sense. So now what we have is that for lags h, which are going to be greater than p, well, what happens? We'll say if we assume that the least squares estimator is, I say assume because I really don't want to have to compute it myself in full generality. So we're just going to use our intuition and extrapolate from what we did in the AR1 case. If you don't believe me, I guess we could try to go through it in more excruciating detail. P x t minus p. But I think this intuitively makes sense. Much like I said last time, if we want to predict xt given the previous p measurements, even given more measurements, right? Because effectively what I have here is I have, I'm going to write it in green. Technically, I have a bunch of other stuff like 0 times xt minus p minus 1 plus 0x t minus h plus 1. Because remember, what I'm actually trying to do is I'm trying to predict xt hat. I'm trying to predict xt. I'm trying to compute xt hat, which is a prediction for xt. And I'm trying to do that based on the previous h minus 1 observations. Now, based on this equation here, the autoregressive equation of order p, it tells me that, well, if I just take the previous p observations, that's about as good as I can do, right? Because I take those p observations, I multiply by their phi, the corresponding parameters phi, and then I can use that to predict what xt is and get my xt hat. And then the claim that I'm not going to go through and prove is that anything prior to that is irrelevant. These green terms that I drew down here at the bottom and multiply by a coefficient of 0. This very much is like the idea of a Markov process. I mean, the Markov process would be the one above, the AR1, where if I know the previous time point, I don't need to know anything else to be able to predict the current time point. This would be a more general pth order process where if I know the previous p terms, that's all I need to predict the current term. And anything further into the past is irrelevant. Of course, this is also assuming that I know exactly what the phi's are. Now, we haven't talked about estimating phi from the data. This is still not proper statistics yet because we're assuming we know what phi is. And in the next section, we'll be doing that. We'll be trying to estimate phi. But for now, we're going to just ignore that because there's a couple different things we're doing here. And in this case, we're just trying to understand what the PACF function would look like. So, okay, that was my rant about trying to say that this is the correct way to predict or to write down x hat t without actually trying to solve the least squares equation for p parameters, which I don't really want to do. And therefore, by symmetry, we would have that at t minus h. I guess I'm doing it backwards now. Before I was doing, no, this is about the same. We're good. We would have the exact same coefficients, but we would be going forward in time. So we would have a t minus h plus 1. This is sub 1. All the way up to phi p. xt minus, I guess, wait, which one are we doing? Oh, this is going to be annoying, I see. T minus h plus p. Yes. Yeah, the most recent, or the most recent t or h, p time points coming after t minus h. So t minus h plus 1, plus 2, plus 3, all the way up to plus p. Okay, good. And then, yeah, in fact, in some sense, we don't even really need to write that down because, well, no, it is good to write that down just to make sure that we're clear what we're doing. But therefore, when we compute the correlation between xt minus x hat t, I'm not going to write that out again, and x hat t minus h, not x hat, x t minus h minus x hat t minus h, then what I get is simply the correlation between white noise at time t and this whole thing. And this whole thing on the right hand, in the right hand argument, is a causal linear process. It does not depend on WT because WT occurs in the future, so it's 0. And once again, therefore, the PACF is equal to 0 for ARP if H is greater than P. And that means we can use the partial autocorrelation function to try to determine the order of an ARP process, because as soon as we cross that threshold of P and we get to P plus 1, it goes to 0. Now, statistically, it's not going to be exactly 0. It's going to be a small, noisy value, because there's always going to be a little bit of white noise in there. It could be above or below when we try to compute it. But the point is that we can look to see when the partial autocorrelations become negligible, or very close to 0, and we can use that to determine the order then of our autoregressive time series. Yes. On the other hand, I'll say computing the PACF for lags less than or equal to P is hard in general. So it's not something that we're going to do, unlike last time in the AR1 case where I actually explicitly computed what the partial autocorrelation is at lag 1. Well, that's, I guess, kind of trivial anyway, because it's just going to be the autocorrelation at lag 1. But the idea is that if I took something else, I would have to compute a least squares estimator. It wouldn't be as straightforward as this one here. So there'd be a couple steps involved. Compute least squares estimator, then compute the correlation based on that. It's doable, but it's going to be probably a pain. I assume it's doable just based on the mathematics. I actually haven't tried it myself, so it may actually be intractable. But I don't particularly care. What I care about is being able to use the PACF function to determine the order of the ARP process. And now, before we look at some examples, we should also see what happens when we take a PACF and apply it to an MAQ process. Get a better looking Q there. There we go. All right, so once again, let's consider just the MA1. Once again, consider MA1, because one term is complicated enough. And this is going to look like xt plus wt plus theta, wt minus 1, and again, with theta less than 1, so invertible. So it's invertible. Remember, this is kind of like the dual property to the causality that comes out of an autoregressive process. We want an invertible process, MA process, because we're going to, well, invert it. Yeah, almost. Therefore, we can write xt equal to wt plus the sum of from 1 to infinity of theta to the I xt minus I. So again, the invertible process is saying I can write white noise wt as an infinite, I guess, linear combination of my x's going back into the infinite past. Now, all I did was do that, but kept xt on the one side and wt on the other side. So, therefore, once again, we get that for trying to predict x hat t from the previous observation, x t minus 1, well, we're going to get, in some sense, the exact same thing we did last time. We get that beta hat is going to be the ratio of the autocovariance at lag 1 to the autocovariance at lag 0, which is just going to be beta hat as theta divided by 1 plus theta squared. This is, simply what we're saying is that if I wanted to compute, say, something like the partial autocorrelation at lag 2, then what I would need to do is take xt and predict it, that is, based on xt minus 1. So I get this exact same equation as last time with a single beta hat. I can solve for the beta hat the exact same way I did last time. The only difference is now k is different. The autocovariance is no longer the autocovariance for the AR process. It's now the autocovariance for the MA1 process, which gets us this new value for beta hat. All right, so now that we have that, well, we can just fight our way through computing a covariance, or I guess a correlation. Well, covariance. Yeah, so now if I compute the covariance between xt, I want the covariance because it's easier to work with than the correlation, and then we can always normalize at the end if we really want to. If I compute the covariance between xt minus xt hat, which is going to look like this, and xt minus 2 minus xt minus 2 hat, which is the same thing, again by symmetry as we saw last time, we get the exact same thing here, xt minus 1. I always do find that a little bit surprising, right? That you're kind of predicting t and t minus 2 using the exact same thing because of this peculiar symmetry. But anyway, what we end up with is something that's going to look a lot like what we had last time, but not exactly. So what happens now? Well, now when we compute this covariance, we're going to use the bilinearity of covariance, and we're going to compute the covariance between each pair of one of those guys with one of these guys. Right? So when we do that, well, the first one is going to be xt minus 2. Maybe I should just write this all out so that all of you listening from home will, hopefully it won't be too confusing. Not expected value, sorry. The covariance between xt and xt minus 2. And the covariance, well, bilinearity, so I'm going to take out that coefficient, and we're going to have xt minus 1, and then we're going to have another thing that looks kind of like that, but we're going to get a minus sign over here, and we're going to get a minus. Oh, I should have had a minus sign there as well. Minus that, and then we're going to subtract the next guy. The next guy is going to be theta 1 plus theta squared, covariance of what? Xt minus 1 and xt minus 2. And the very last term is going to be theta squared over 1 plus theta squared, and the covariance between xt minus 1 and t minus 1. Phew. All right, so we got all of that. What in the world is this? Well, we can replace these with a bunch of k's because it's stationary. So we get a k at lag 2. We get a 2 theta over 1 plus theta squared at lag 1. And we get a theta squared over 1 plus theta squared all squared, and a k autocovariance at lag 0. All right, so now we've got 3 things going on here. What in the world is that? Well, we can actually just plug in the values that we know, right? Because we already know what the, double checking this. Yes, we already know what all of the autocorrelations and the everything should be. If I remember off the top of my head, let's see if we can do this from memory because I didn't actually write it down. At lag 2, the autocorrelation is 0. At lag 1, the autocorrelation should just be theta. Yes, just should be theta. So we end up with something like 2 theta squared, 1 plus theta squared. And over here, we should get a 1 plus theta squared, which means I get a theta squared divided by 1 plus theta squared because one of them in the denominator cancels out. And when I put this all together, I get a minus theta squared divided by 1 plus theta squared. And yep, that's exactly what I had written down. Good. All right. So what were we doing? Oh yeah, we were trying to compute the partial autocorrelation here. So what we did was we got the covariance. We're almost there. We're doing this in 2 pieces. We've got compute the covariance, compute the variance, divide one by the other, and we have the partial autocorrelation. So that's step 1. Put a little dot up here. And then we'll put another dot down here and then say step 2 is compute the variance so that we can have something for our denominator. We want just xt theta over 1 plus theta squared xt minus 1 here. And when we expand this thing and we compute the variance, basically, well, what do we get? We're going to get at lag 0. We're going to get 2 things. We're going to get the first term squared, which is just going to be a coefficient of 1. And the second term squared is a coefficient of theta squared over 1 plus theta squared all squared. Yeah, I think that looks good. And then for the cross term, when we do xt times xt minus 1, we're going to get a minus sign. We're going to get, well, 2 of them, right? Yeah, so I'll just write this down first. We're going to get the autocovariance at lag 1, and we're going to get a coefficient of 2 theta over 1 plus theta squared. There are a ton of derivations in time series, aren't there? You think it's all going to be just like, ooh, cool, stocks. Let's calculate a whole bunch of stuff and see if we can predict the market. No, it's a lot of thetas and phis and keeping track of all of them. Anyway, where were we? Yep, now what we do is we just plug in our definitions. So we have, again, for this guy, we would have a 1 plus theta squared. For this guy, we would just have a theta itself. And we end up with something that's going to look like 1 plus theta squared plus theta squared divided by 1 plus theta squared minus 2 theta squared over 1 plus theta squared. All right, and yeah, no, we can simplify this a little bit. If we, well, I'm just going to skip the step and we're going to simplify it to be 1 plus theta squared plus theta to the 4th divided by 1 plus theta squared, right? Basically what happens is this guy cancels out with that 2. And then I can divide this by 1 plus theta squared and multiply it by 1 plus theta squared. And then I just shove all that stuff together. The minus theta squared over on the right side cancels out with one of the theta squareds that comes out on the left side here, and we left with this kind of crazy looking expression. Okay, now we can actually finish this, right? Because what we're going to do is we're going to say, therefore, with a big therefore, ... the PACF, or what I should write is, to use our math notation, phi x, script phi x, that is, at lag 1 is going to be what? Well, it's going to be minus theta squared 1 plus theta squared divided by 1 plus theta squared plus theta to the fourth divided by 1 plus theta squared. The theta squareds cancel out, and the 1 plus theta squareds, I should say, cancel out, and we're left with a minus theta squared over 1 plus theta squared plus theta to the fourth. Whew. And then this guy is the PACF for an MA1 process. Yeah, I'm definitely not doing MA2 or 3 or MAQ for that matter. But yeah, basically, what are we getting here? The point is that the PACF for MAQ decreases to 0, but, well, I guess it doesn't strictly decrease to 0. It might alternate because of the signs. It, in magnitude, I didn't prove that, I just kind of am going to claim it, but doesn't vanish, i.e. it doesn't actually equal 0 at any point. So that leads us to a table, which I'm going to write down, and then we're going to actually look at some examples. So in summary, we have ACF, we have PACF, we have ARP, and we have MAQ. So what happened in this case? All right, we still got seconds or so. This basically decreases geometrically. In this case, we also get a decrease geometrically. I didn't actually prove this one. Not that I strictly well, I guess the other one we kind of showed it. But and more so, you can just trust me on that one. It decays to 0, but it does so in some asymptotic or geometric sense. Over here, it is equal to 0 for h greater than q, and here it's equal to 0 for h greater than p. And thus, we're going to use these tools to try to figure out what our actual time series data is doing by estimating the ACF, by estimating the PACF, and staring at it and trying to get some sense about what's going on. So let's do that now. And we're back. We're in our studio now. Let's see what this PACF and ACF functions are really going to be able to tell us about our time series. So first thing we're always going to need if we're going to be generating some time series data is we need some white noise. And our white noise now will be our norm. Let's say 500. Let's do 500. We need an AR1 process. So we're going to use the filter command. And the filter command, we're going to stick in our white noise. We are going to tell it to give us a coefficient of, let's say 0.7, something big enough that we can obviously detect it. And the method is going to be recursive, if I can spell that correctly. Good. Then we're going to do the same thing for an MA1 process. I'm going to keep the same coefficient of 0.7. I think I need to tell it. Let's see if this works. Recursive and convolution, I think it was. And there's one other argument I'm going to need, which is sides. If sides is equal to 1, the filter coefficients are for the past values only. If they're 2, they're centered. So I want the past values. So I think that should have given me what I wanted. Let's double check the filter command. Yeah, the convolution filter is going to be T plus O plus the offset all the way to offset, where offset comes from the sides. So is that what we want? I think that's what we want. Well, we're just going to check it. I think I might have to put a 1, 0.7 to get what I want, but why should I take a guess when I can just use the ACF function that we kept talking about? See, now in that case, this looks more like white noise, which means I made a mistake. What I should be doing, I think, is put a 1 there. So effectively, I'm taking the current time and giving it a coefficient of 1, and then taking the next time point, the previous time point, the white noise that is, and giving it a coefficient of 0.7. Of course it has missing values. That's sort of the whole point. Okay, NA, We'll just get rid of the first value. There it is, okay. All right, so we got kind of what we want. That's right, of course, it's not going to be exactly 0.7 like it is in the ACF case, so we're good. I just needed to modify my R code here to make sure that I'm actually producing an MA1 process and not just a scaled white noise process like I did up here, where I didn't put the 1 in. And we already got our first result, which is, well, look at that. Of course, we have an autocorrelation of 1 at lag 0, but we have something that's about 0.5 or so when we have for lag 1. Now, if I recall off the top of my head, I think it should be something like theta divided by 1 plus theta squared should be the value. And sure enough, that value is 0.469. So basically 0.47. And I don't know exactly what this is. We could compute it exactly from our data, but it looks pretty close to 0.47. So yeah, it looks like our ACF is doing what it's supposed to be doing. Now, similarly, well, maybe not similarly, but in contrast, if I plug in my AR1, I get that nice geometric decay that we talked about. It starts at 0.7, then it goes to that thing squared, which is going to be about 0.49. Then it goes to whatever 7 cubed is, which I kind of forget off the top of my head. I guess 340, whatever. Doesn't really matter. 343. Yeah, 0.343, and then so on down the line until we get down below the noise floor. So notice that we do have a nice geometric decay. Eventually, though, we start to just get random fluctuations here as we move off to infinity because, well, the actual ACF value is equal to some very small number, positive number, but because there's noise in the system, we don't quite capture it. We actually could plot this if I said lines and said, let's say, I don't know, 1 to 15, and then said 0.7 to the 1 to 15, and then gave it a color like red so we can kind of see what's going on here. Yep, and there it is. So that's what the actual autocorrelation should be doing. And the black lines, remember, are estimates based on our 500 data points. And that's what they see. So that gives you an idea of what the true autocorrelation should be. I guess we could have started it at 0 to get the full effect of the geometric decay. Yeah, that looks better. Right, so you can see the red line is what the autocorrelation is doing in mathematics world. The black lines are what the data is telling us it looks like it's doing. But the important thing is it lines up with what we would expect. Now, if I switch to PACF, hey, that's pretty good. Except that one thing to note is that we didn't actually compute the PACF at lag 0, as I mentioned. So we're starting now at lag 1. We only have one lag, that is lag 1, that has a spike that's anything larger than our noise floor. And it's about 0.7, really close to 0.7 here. So it's exactly what we saw from before, which is that the PACF function should tell us exactly what phi is equal to, in this case, 0.7, at least for the AR1 process. In contrast, if I plug in an MA1 here, it's going to yell at me because I forgot to delete the first NA entry. And then, well, we get something alternating and decaying geometrically. So this is kind of neat. It's doing what we saw in the equations. The sign is flipping, so it is decaying in a geometric fashion below the noise floor, but the sign kind of flips where it goes positive, then negative, then positive, then negative. And we saw that a little bit when we wrote that equation on the previous, in the notes, where we had that sign flipping happening. All right, so that's PACF and ACF, but let's go a little bit further because, okay, we already kind of know what the MA1 and the AR1 look like. Let's see if we can take this up a notch to an AR3. And then I'm going to try really hard to pick some coefficients that are not going to give me a non-stationary or non-causal process. We'll see if I can make it work out. Let's just plot it to make sure it doesn't look like it's going to explode. Nope, looks good. There is a function in R that allows you to compute the roots of polynomials. I forget what it is. It might very well be roots. Nope. Maybe poly, or no, poly does orthogonal polynomials, which you can use in various places in statistics. So I'll look it up later. I know I have it somewhere in my notes for later in the course, so we will look at that then. I'm going to put the exact same coefficients in here just to contrast what's going on. I think it should still be fine, except I'm going to have to delete more entries when I try to compute these things. So now if I compute my autocorrelation function for my AR3 process, well, it can be deceiving, right? Because it's supposed to be geometrically decaying to 0. And I guess in a way it does, but it also looks like it vanishes after lag 1. So when you see this, you might think to yourself, that could actually be an MA process. But in our case, it's actually an AR3 process. We're actually going to find out later that you can flip MA and AR processes too. So just to make estimation even more of a headache, if you're trying to estimate an MA as an AR, you can do that. And an AR as an MA, you can also kind of do that too. So yeah, there's a lot of weird headaches in time series. But at least when we stare at this, the first thing we might think is we have an MA1 process, but no, actually we have an AR3 process because that's how I generated this data. So again, this is useful, but we also have to be a little bit careful. Now, if we go to the PACF and look at this, we say, look, well, this one seems to vanish also after lag 2. So that's kind of interesting because here we actually have 3 an order 3. I mean, up here we have an order 3 process, but this third coefficient, I guess, is kind of small, and it doesn't really detect that we have an AR3. it kind of looks almost like we would have an AR2. So again, these are some of the shortcomings of these methods. It's good to look at, it's good to understand, but you also have to think a little bit on your feet and not be too stringent or strict with the rules, right? These are supposed to guide you, but not tell you the answer, but help your intuition, I guess, guide your intuition. Let's look at that MA3 process. And it's going to yell at me, of course, because I have to say delete the first 3 entries because the first 3 entries are NAs. And now we get something. Well, remember, what's it supposed to do? It's supposed to vanish after order 3. So we have, well, at 0, it's 0. Then we have 1, 2, 3, and then nothing. So it kind of works, but some of these spikes are so small that you might even consider that they are not significant. They're not significantly above the noise floor anyway. So again, this can give us some evidence as to what's going on here, but it's not always clear. And if we compute the PACF function, wow, okay, so we got something crazy going on there. But we do see some interesting stuff. We see some alternating terms, and we do see some decay to 0, even though it's not completely going to 0. So that one at least is kind of telling us maybe we do have an MA process here. Why don't we look at them all at once? While we're rolling with this, we say MF row C2, and then we're just going to plot all of them. So we're going to get ACF AR3, PACF AR3. We're going to get, what is it, ACF MA3 and PACF MA3. All right, so this is what we have to work with. Again, it's not always straightforward what kind of time series you have, even given these rules of thumb that we talked about in the notes. But it is still useful to know what you might see and how they might differ. The bottom, an MA3 process, the top, an AR3 process. So especially in the PACF plots, the right column, we definitely see some difference. The ACFs are not obviously that different. I mean, yeah, you get a slightly different spike here, but it doesn't seem to be too different. Whereas at least over here we just see one alternation. Here we see a bunch of alternations. So we do see something that looks a little bit different, at least on the PACF plots. And if that wasn't confusing enough, what would happen if we actually had an ARMA plot? Now, I didn't actually prepare this beforehand. I'm pretty sure there's a way to generate ARMA data. I just forget what it is. And of course, it's not going to tell me. It's probably ARIMA. But ARIMA fits the ARIMA model. There it is. ARIMA sim is what I want. So what we can do, let's see if we can do this without me messing this up, since I'm doing this on the fly. We'll say ARMA 11. And to generate that, what I need to do is I need to give it a model. The model is actually going to be a list with components AR, and AR is just going to be, let's say 0.7, and MA is going to be minus 0.5. And I guess we'll just ignore, I think everything else should be good. Oh, we have to tell it, we need to tell it how many data points we want. So let's say 500. N is 500. I'm going to make sure it knows that this is the model, even though it's the first argument, so we should be good. Our noise is going to be random. Let's see if that works. Okay, that looks like it could be an ARMA plot. Why not? Let's do one other thing. We need to use the par function to set this back to a single plot, because I don't like looking at the one up in the corner. I want to get a nice big plot of our noise, of our time series, that is. And lastly, what I want to do is actually check to make sure I simulated this thing correctly. And to do that, I'm going to use the ARIMA function and try to fit a I'm going to try to actually fit a model to it, and I should get two coefficients. Well, I'm going to tell it to give me two coefficients, so it better give me two coefficients, but it should get something close to 0.7 and 0.5. And yeah, that looks pretty good. 0.7, and I should say minus 0.5. So just using the ARIMA function in R, I was able to at least show that, yeah, I simulated this data correctly. So again, a priori, we wouldn't know what the order is. We would have to be looking at things like AICs and log likelihoods to try to get a sense of what the order for our time series process actually is, our ARMA or our ARIMA model. But in this case, let's just look at the ACF and the PACF and see what we get. I actually could have used this function to simulate the AR and the MA process more easily than the filter process, but that's okay. Anyway, let's look at ARMA 1.1 and say ACF. Well, okay, so once again, it's not clear exactly what it's doing. What it's doing is, well, it has a few non-zero spikes, and then it falls below the non-negligible spikes, then it seems to fall below the noise floor. If we look at the PACF, let's see what we get. We get, yeah, so at least one spike above the noise floor. I don't know what's happening with these two, and then the rest kind of disappear. In general, what we should have is something that decays geometrically in both arguments, or not both arguments, in both the ACF and the PACF. Again, because we're estimating this from real data, it's not always clear. What we could do, I guess, is go back to where I generated the data. And yeah, we're about done with the lecture. So let's just stress my computer out and see what we can do. Instead of 500, let's give 50,000 and see if that just is super annoying to work with. There we go. Now that looks a little bit better. So by giving it 50,000 data points, we can much more clearly see the geometric decay. I mean, when we, you know what I should do? I should, let me load in that library. I think it's TSA has the alternative version of the AR, the ACF, yeah. There we go. So now if we ignore the lag of at the ACF of 1 at lag 0, here we actually can see that we do have quite a geometric decay, the way it looks, with the way it's kind of going down, but it's decreasing as it gets closer. And if we go back to PACF, we should say something similar. Yeah. So once again, we do see something similar. So I guess the moral of the story is that it's not always clear from your data what you have going on with the ACF or PACF, but if we have an absurdly large amount of data, then we can get a much clearer picture of what's happening with our time series. If we see geometric decays in both the ACF and the PACF, it's telling us we'll probably have an ARMA process. There's an MA and an AR piece that we have to work with. If we see that it drops off immediately at some order, in the ACF, that's telling us we're in an MA setting. If it drops off immediately in the PACF, then we're in an AR setting. And wherever it drops off is kind of hinting at what the order should be. So with that alphabet soup over, I think we're going to stop for today. Hopefully that was kind of clear. These are really good tools to play around with. So I'd encourage you to try to simulate your own data and see what it looks like after running this code on it. And while you do that, think about all of this, and we'll be back next time. And next time we'll be starting the next chapter in my notes, which is great because we're actually going to be doing estimation. So far, we haven't actually talked about estimating coefficients for these models, besides me just running this command and not telling you where those numbers actually came from. But we're going to find out where those numbers come from in the next lectures. So see you there.